We finished our discussion of transformer circuits in our last lesson when we were looking at the impedance in the secondary. And we came up with this formula that said the impedance in the primary was going to equal the primary windings divided by the secondary windings squared times whatever the impedance was in the secondary. And we're going to apply that in a circuit in just a moment. But before we do that, I just want to mention a little bit about what is impedance. Impedance is, when we talk about resistance, impedance is a term that is commonly used to talk about resistance in an AC circuit. When you just say resistance, sometimes it can be applied to both. When we talk about impedance, typically we're talking about resistance in an AC circuit. So let's look at, here we have a transformer and a load, and we're going to do a few calculations with this. First of all, this is the formula that we just came up with. We said that the primary one divided by the secondary one is squared times the secondary impedance would tell us the impedance of the primary. And so, as I mentioned earlier, here we have 100 ohms in the secondary. Usually the secondary resistance or impedance is just, it's a known value because you can see it right in the circuit. So let's do some calculations here. The primary to secondary is a ratio of 10 to 1, so we would see 10 to 1 here. And the secondary impedance is 100. So we would have, and remember this is squared, so this is going to be 100 times 100, and that is in fact 10K. So what that's saying is that the impedance that the primary is going to experience here, looking into this circuit, is going to be 10K ohms. Now you notice there's no resistor here, but this is the impedance that it will experience as a function of looking through these windings at this particular resistance. And if this resistance were to change, then this impedance would also be impacted. But let's do a little bit of calculating here to prove this. First of all, let's look at what is the voltage in the secondary. And we can see 10 to 1, let's see, we have 120 volts applied, we have a 10 to 1 drop, so we would have 12 volts in the secondary. So let's see, what is our current in the secondary? So we take 12 divided by 100, and let's see, do we have our calculator handy? If we say 12 divided by 100, we're going to get 120 milliamps of current. So we'll say 120 milliamps. And let's calculate the power that's dissipated in this transformer. So we would say, remember, power is E times I. So we will say 12 volts times 12 milliamps. And let's see, what will that equal? We've got, just a moment here, let me get this back on track here. Okay, so we would say we have 120 milliamps times 12 volts, and that would give us 1.44 watts. So we have 1.44 watts. Now, something we could do, we could take this value and use it to solve for what is the current and power that we have over here. So we know that we have 120 volts applied, and we know that we have 1.44 watts in the secondary, and so we know that 120 volts times whatever the current is going to equal this value, because remember we said that the power in the primary equals the power in the secondary. So if we wanted to solve for I here, we could, well, let's see, we could say divide this by 120, divide this by 120, and then cancel this, and then I would equal this divided by 120. So why don't we do that? And so we could say 1.44 divided by 120 will give us 12 milliamps of current. So I in the primary is 12 milliamps. So now we could solve for power here. So we could say 120 times 12 milliamps, and let's see what that is. If we go, here we already have 12 milliamps on the screen, times 120 volts, and we'll see that that equals 1.44, and that was our original power calculation. Okay, we could have done that another way. It would have been a lot simpler, actually. We went in and we we calculated the impedance. We said it was 10K. Well, what we could have done, we could have just said 120 volts divided by 10 exponent 3, and we would have gotten the same value, the 12 milliamps. So that would have been a quicker way to do it, but I wanted to walk through it showing the power calculations. And so anyway, that does prove that our formula here actually does work. Okay, impedance of a secondary is reflected into the primary. Now, we've already actually mentioned this. Your text goes into this discussion, so I'm going to allude to it. Transformers change voltage and currents depending on turns ratio. It only makes sense that if voltages and currents are impacted, resistance or impedance will also be impacted. And the discussion follows on the next slide. Your text goes into a discussion about reflected impedance using the 3 illustrations to the right, and so they use these 3 illustrations. And the point of the discussion is that as resistance changes in the secondary, current will also change, and this change will be reflected in the primary. And actually, we proved that in that last circuit, but the gist of that is that here they start out with a high resistance, the resistance goes down, and then the resistance goes much lower. Well, what's going to happen is as a result of this changing resistance, current is going to increase in the secondary. And if the current increases in the secondary, then the current must also change in the primary. But the fact is that there is no resistor in the primary. The resistance that is experienced in the primary is a function of the turns ratio and the resistance that you see in the secondary. And that's mentioned here about remember we talked about how the power in the primary equals the power in the secondary. So if the secondary current goes up, then the primary current must adjust. Okay, so let's do another calculation. And here we have, this is a virtual audio transform. This is one from Workbench. And this particular one has a 2-to-1 ratio. And we're showing 169 volts here. Now that is a peak value. Actually, this is 120 volts if we consider RMS. And this is what you would see out of the wall. That is actually, if you measured it with an oscilloscope, that's what you would see as the peak value. So what do we want to do? We want to calculate the impedance in the primary, the current in the primary, the power in the primary, and the secondary power. Okay, so let's see. Where are we going to start? This was our formula that we had used just on the previous calculation. So let's use this again. So we start out with the turns ratio between the primary and the secondary, which is 2-to-1. So we would say 2-to-1, and we're going to square that. And then we're going to take it times the impedance of the secondary. In this case, this is 50 ohms. And so let's see, we have 2 squared, which is 4, times 50, that's going to give us 200 ohms in the primary. Now we could, let's do it the quick way this time. We want to know what is the current in the primary, so we could say 120 divided by the 200 ohms that we calculated. We calculated the primary impedance, and so let's pull up our calculator. Let's see where there's our calculator, and if we say what do we got? 120 divided by 200 equals 600 milliamps. Okay, so we have 600 milliamps here, and if we wanted to calculate the primary power, we would take 120 volts times the 600 milliamps, and let's take a quick look at that. 600 milliamps times 120, and that will give us 72 watts of power, and that should be the same thing that we're seeing in the secondary. So let's do our secondary calculation. Let's see, what do we have as a our voltage in, we didn't even talk about the voltage in the secondary, but it's a 2-to-1 ratio, and so we have 120, so it's going to be about 60 volts in the secondary. So if we take 60 volts and we divide that by the 50 ohms, we will get a current of 1.2 amps, and then remember to get power, we'll take that current times the voltage times 60 volts, and there we have it. We have 72 in the secondary and 72 in the primary. Now on the next screen I have this is actually a multi-sim calculator, this is a multi-sim circuit that you see here. This is the same one that we just looked at right here. Okay, you'll notice the 169 here and the 50 ohms. This is the same circuit. I put a voltmeter in here, and these are the actual values that Multisim gave. Notice it's 59.92. Remember the input was 120. The turns ratio was 2-to-1, and so divided by 2, that would have been 60. But you'll notice it's very close. But Multisim is really quite accurate, and the turns ratio wasn't perfect, so you would see a little bit of a drop here. And then we calculated the power, and in our calculation we said there was 72 watts. And you'll notice here that the calculation is very close. That's 71.39 watts. Now, if you do this simulation actually in Multisim and you attempt to measure the current in the primary, that simulation that comes with your textbook, the circuit that they have, one of the circuits in this particular chapter, I had great difficulty in getting the multimeter to measure current in the primary. And sometimes simulations don't always work perfectly. What I have here is actually a watt meter, and in your Multisim package you do have a watt meter. Okay, next item here, troubleshooting transformers. In general, common defects in transformers are, notice an open primary, an open secondary, shorted turns or shorted windings, windings shorted to the core, short between the primary and the secondary. In fact, these four here we had talked about in previous lessons, and this is about the only one that's new here, is a short between the primary and the secondary, and that will end a transformer. Defects in a transformer can be detected by observation or by checking with an ohmmeter or a voltmeter. Okay, so in this section we looked at some circuit calculations, and in your homework at the end of the chapter you'll find you'll have quite a number of calculations that you can perform to get the feel of transformer calculations.